This first mini-lecture introduces stoichiometry, an approach for quantifying the amount of each chemical species in a reaction based on the quantity of a single reactant or product. Recall from our initial introduction to moles that a molecular formula can be interpreted as the number of atoms of each element in one molecule of a compound, but it can also be used to determine the number of moles of each element in one mole of a compound. So in the case of isopropyl alcohol seen here, which has a molecular formula of C3H8O, we know from the formula that in 1 mole of isopropyl alcohol, there is 1 mole of oxygen atoms, 3 moles of carbon atoms, and 8 moles of hydrogen atoms. The molar amounts of each element in the compound can also be expressed as molar ratios or conversion factors, giving 1 mole of oxygen per mole of isopropyl alcohol, 3 moles of carbon per mole of isopropyl alcohol, and 8 moles of hydrogen per mole of isopropyl alcohol. Using dimensional analysis, these conversion factors could be used to solve for the moles of oxygen, carbon, or hydrogen when a very specific number of moles of isopropyl alcohol is provided. Or we can write conversion factors that give the mole ratios between the different elements, such as 1 mole of oxygen per 3 moles of carbon, or 3 moles of carbon per 8 moles of hydrogen, or 1 mole of oxygen per 8 moles of hydrogen. And remember that any of these mole ratios over these last 2 slides can be written with the numerator and the denominator switched. So these conversion factors can be used in dimensional analysis to solve for the moles of one element in a sample of isopropyl alcohol if the moles of a different element are already known. Also remember that since these conversion factors represent a per particle basis and the mole just represents a specific number of single particles or molecules, then the conversion factors will be the same if considering single atoms within one molecule or moles of atoms within a mole of the molecule. All of these concepts for single molecules can now be simply applied to several molecules in a reaction. When interpreting a chemical reaction, it is important to remember that the reaction shows the per particle picture that we are unable to see with our eyes. So in this reaction between carbon monoxide and hydrogen gas, the coefficients in the balanced reaction are indicating that 1 carbon monoxide molecule reacts with every 2 hydrogen molecules to produce 1 methanol molecule. These numbers can be scaled to larger amounts simply by multiplying the coefficients by the same value. So if I multiply the coefficients in the reaction by Avogadro's number, there would be 6.022 times 10 to the 23rd molecules of carbon monoxide that would react with 12.044 times 10 to the 23rd, or twice as many molecules of hydrogen to produce 6.022 times 10 to the 23rd molecules of methanol. Now, since we know Avogadro's number is equal to 1 mole, then we can also write this as 1 mole of carbon monoxide molecules reacts with 2 moles of hydrogen molecules to give 1 mole of methanol. So notice how the coefficients in the balanced reaction give the per particle ratios, and they also give the per mole ratios. However, be very careful that you never assume that the coefficients give the per mass ratios, as they cannot be interpreted as 1 gram of carbon monoxide reacts with 2 grams of hydrogen to give 1 gram of methanol, because the molar masses of each compound are very different from each other. So their per particle or per mole ratios do not match their per mass ratios, and the reaction should never be interpreted in this way. As we saw on this previous slide, we can use the molar coefficients in the balanced reaction to predict how many molecules would be involved in a reaction if you change the amount of one chemical species. For example, in this water decomposition reaction, 2 molecules of water form 2 molecules of hydrogen and 1 molecule of water. But if I started with 4 molecules of water, then I would produce twice as much hydrogen and oxygen since I'm starting with twice as much water. So the 2 molecules of water becomes 4 molecules of water. The 2 molecules of hydrogen becomes 4 molecules of hydrogen, and the 1 molecule of oxygen becomes 2 molecules of oxygen. With simple whole number factors, we can simply scale up the molar coefficients to get a new molecular picture for the molecules in the reaction. However, not all values that we work with will be this simple, and when dealing with moles, it becomes increasingly difficult to visualize the actual number of particles since a mole is such a large number. So, what if we wanted to know the number of moles of hydrogen and oxygen produced by the decomposition of 5.8 moles of water? For this, we should first write the mole ratios for the chemical species in the reaction based on their molar coefficients. Since there are 2 moles of hydrogen produced when 2 moles of water reacts, this can be written as 2 moles of hydrogen per 2 moles of water. And since there is 1 mole of oxygen produced when 2 moles of water reacts, this can be written as 1 mole of oxygen per 2 moles of water. Then we use these conversion factors in dimensional analysis to convert the starting amount of 5.8 moles of water into moles of hydrogen and moles of oxygen produced. For moles of hydrogen produced, we start with the 5.8 moles of water that are reacting and multiply it by the mole ratio expressed as 2 moles of hydrogen per 2 moles of water. Note that the moles of water unit cancels out, leaving us with 5.8 moles of hydrogen produced. The mole ratio between hydrogen and water is 2 to 2, but it may also be referred to as a 1 to 1 ratio because the number of moles of hydrogen produced will always match the number of moles of water that reacted. That is the basis of a 1 to 1 ratio. For moles of oxygen produced, we again start with the 5.8 moles of water that are reacting and multiply it by the mole ratio expressed as 1 mole of oxygen per 2 moles of water. Again, note that the moles of water unit is going to cancel out, leaving us with 2.9 moles of oxygen produced. So, to go from moles of one chemical species in a reaction to moles of anything else in the reaction, all you need is the mole ratio between the 2 chemical species, which comes from the coefficients in the balanced reaction. We also saw previously that the molar mass of an element or compound can be used to convert moles to grams or vice versa. So by considering just a few extra conversion factors, we can also use the coefficients in a balanced reaction to determine the masses of each reactant and product involved in a reaction when the mass of one thing is known. Note that masses are more practical values in the lab setting, as we typically measure masses instead of moles. So it is very important to know how to adapt the mole-to-mole conversions we just saw previously into mass-to-mass conversions. Next, we'll consider a more complicated reaction, the combustion of propane. We want to solve for the mass of oxygen that is required to completely combust 96.1 grams of propane, or C3H8. But first, don't forget to check that your reaction is balanced. In this case, the reaction we were given is not balanced, and if we were to proceed with our calculations without balancing it, they would be incorrect. So from here forward this semester, whenever you are given a reaction in a problem, always check if it is balanced before doing anything else in the problem. Next, before we can use the molar coefficients in the reaction for the mole ratio between the propane and the oxygen, we first need to determine how many moles of propane we are trying to react, because we were given 96.1 grams of propane. So to convert this to moles, we use the molar mass of propane as the conversion factor. And this type of calculation is something we covered earlier in the semester, so it should look pretty familiar. Here we see that 96.1 grams of propane is equivalent to 2.179 moles of propane. Now that we have the number of moles of propane that are reacting, we can use the mole ratio between oxygen and propane given by the molar coefficients in the balanced reaction to convert moles of propane to moles of oxygen. And we see that 2.179 moles of propane will require 10.89 moles of oxygen to fully react. But we want to know the mass of propane, so we do one final conversion from moles to mass using the molar mass of oxygen as the conversion factor. So combustion of 96.1 grams of propane would require 348.6 grams of oxygen. If you take the ratio of the masses, you'll note that it does not match the 5-to-1 ratio of the moles for these two compounds, which is why converting to moles to use the mole ratio is crucial. Notice how the steps to solve this problem followed a particular sequence, where first we converted from grams to moles using molar mass of the first chemical species, then from moles of one chemical species to another using the mole ratio between the chemical species given by the coefficients in the balanced reaction. And then we finally converted from moles back to grams using the molar mass of the other chemical species. This sequence of steps will be the same for any chemical reaction when you are starting with grams of one thing and looking to solve for grams of another thing. We can also string together all the conversion factors in these steps to get one long calculation as shown here. I prefer this method as it usually helps avoid rounding errors after each individual step. Again, notice the pattern here of converting grams to moles using a molar mass conversion factor, using the mole ratio to convert from moles to moles, and then using another molar mass conversion factor to convert from moles into finally grams. So, for a bit of a challenge, pause the lecture and see if you can determine the mass of carbon dioxide that would be produced when 96.1 grams of propane fully reacts. Ready to review? This time, I'm presenting the workflow of this calculation with images, as this is sometimes something that will help students visualize the steps that are involved. Note that the sequence of steps is very similar to the previous calculation, but some of the conversion factors have changed. The mole ratio is now between carbon dioxide and propane, and the final molar mass conversion factor is now for carbon dioxide instead of oxygen. This gives a final answer for this calculation of 288 grams of carbon dioxide that would be produced from fully combusting 96.1 grams of propane. This concludes the first mini lecture for material from Chapter 9. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.